Okay, let's take a look at this example. We have a three-phase ABC sequence, Y-connected source. So your source is a Y. I'm going to draw just one phase of it. This is A. This is N, with the VAN given to us to be 220 angle 0 volts RMS. Supplies power to Y-connected load that consumes 50 kilowatts of power. I like this problem. It says in each phase. Notice there's no guessing here. So here's the load, and that's 50 kilowatts. That's your average power. So the average power is 50 kilowatts. And the power factor is 0.8 lagging. We also found there are three capacitors found that each have an impedance of negative 2J, are connected in parallel with the load in Y configuration. So we have a capacitor here of negative 2J. Each have an impedance of negative 2J. I had to read that carefully because it says each one of them, negative 2J. If it says all three of them equal negative 2J, then you divide this by 3. But each one of them has a negative 2J. And are connected in parallel with the load Y configuration. Determine the power factor of the combined load. So what is the power factor of this one? So this might be easier to solve it in terms of complex power. Let's look at this load here. Let's find out what we know. We know that it's lagging, so it's a positive angle. We know what that angle is the inverse cosine of 0.8. So let me get my calculator here. Third cosine of 0.8, and it's roughly 37 degrees. We know this is 50 kilowatts. We need this one. That's the VAR, V-A-R, Q, the complex value. So to get that value here, it has to be the tangent. So tangent, 37 degrees, equals the opposite, which is VAR. We'll call it Y here instead of VAR. The unit will be VAR over 50K. So what is Y equal to? Tangent 37 times 50, and that's 37.5 kVAR. So now we know what S for this, the complex power, we'll call that load 1. And this is load 2. For load 1, S equals 50 plus J 37.5 kVA. So each one in the thousand. 50,000, 37.5 thousand. It's complex power, so it's VA. This is VAR, this is watt. But when you put them together, that's a VA. So Q for load 1, we'll call it Q1. The imaginary portion, that one, is actually 37,500 VAR. Now this should have a negative because when you put a capacitor in parallel with this, you're trying actually to decrease this value, the VAR value. So your capacitor is going to go like this. It's going to have a negative value for VAR that will decrease this one, and that will increase your power factor. Ideally, you want this one to be right there. Your power factor is 1. That means you're getting everything. You're not going to get it, but we'll get close to it. So let's see what Q for the capacitor, or Q2, is equal to. Again, that's Q for the capacitor, or Q2, whatever you want to call it. Is we know what the voltage across the capacitor. It has to be a negative value because we know Q here. Notice that's a negative 2J. So it's negative. You take the voltage, the magnitude of the voltage, and you square it, and you divide it by Z for the capacitor. If you don't put that, if you just put the Z with the minus sign, minus J, it doesn't work. Because if you don't do that, when you have a negative J on the bottom, it becomes a plus J. So really you need the minus 1 here, and that should be the magnitude of that, because this value has to be negative. So that's a negative 220 squared. I think 220 was it? Yeah. Divided by the magnitude of the capacitor, which is a 2. So let me get my calculator there. Negative 22, oh, that's not negative. 220 squared, I'll put the negative after that, divided by 2. Oh, wait. 220 squared divided by 2. And I got negative 24,200 VAR. So when you put them together, the new Q now is going to equal the old one, if you want to call Q1 the old one, and that's what we called before, plus Q for the capacitor. So the new Q here, the old Q was what? Right there, that's the old one, 37.5 K. Add to it the new Q, which is that number, negative 24.2 kVAR. So what do we have? What's 37.5 minus 24.2 is 13.3 kVAR. Remember, by putting the capacitor, you're not changing the real value. So now, when you look at your complex power, the new complex power, this way you know. You know the real portion still 50K. But now the imaginary one is 13.3 kVAR. Can we figure what this angle is? If you know that angle, that's the new, you take the cosine of that, that's your power factor. So tangent, we'll call it alpha here. It's the opposite, which is 13.3, divided by the adjacent, which is 50. That's 0.266. So alpha is equal to what? The inverse tangent of 0.266. Second, oh no, clear. Third tangent, 0.266. The angle is 14.9 degrees. So what is my new power factor? Because the question determined the power factor of the combined load. So the power factor is going to be the cosine of 14.9 degrees. And what's the cosine of 14.9? cosine, second cosine, 14.9. And now notice my power factor jumped to 0.97 lagging. So you actually move that power factor from 0.8 lagging to almost 97, so from 80% to 97% by putting that capacitor in parallel.